Morning.
Okay, so I would like to start as usual, so ask you kindly to log in on remote computers. And if you are successful, please put your hand on. Do not forget when you are successfully logged in to close all the applications and run console. Even if the console is opened, please close it and run again.
I'm sorry that I wasn't able to get access to any computer, so today
Which one?
I'm only making notes.
Sorry, I can't hear you properly. Could you repeat once more what you said?
Yes, of course. Today I wasn't able to get access to any computer because I don't have my own computer. So today I must doing only note.
Okay.
About
Okay.
us.
I'm sorry for this. So please just be the observer and try to make your notes. Okay.
Yes, of course.
Right.
Excuse me?
Yes.
So if I access the computer and there is a console running and it's someone else's project, I should close it because no one is on the computer right now, right?
Yes, but it is you can save it if you want on the desktop.
Okay.
Right. And do not forget to put your hand on when you are ready, okay? So in the meantime, waiting for your response, I will make a coffee, so I will be back in a few minutes. And I hope that during this time, everybody will be logged on. Okay, congratulations. I see that this time it is very quick. All right, so we will start slightly differently today. I mean that I will give you a project. I will give you a project and you will have half an hour to prepare this project in COMSOL. I won't help you because your job will be to prepare the project based on the notes, based on the experience you have got up to now. And after this half an hour, we will just discuss what you have done. And we will find out where the possible problems are and how to solve them. So this is your project. We have one-dimensional heat transfer problem. We have a heat transfer equation. We have from one side Dirichlet boundary condition, from the second homogeneous Neumann boundary condition. We have fixed initial temperature. We have some data.
I'm sorry, we can't see this project.
You can't see the project. Okay, thank you for this information. All right, so I'm back. So this is a rod. So 1D problem with the heat transport equation. Coefficient K is described as follows: is a function of position. We have boundary conditions on the left, and we have a homogeneous Neumann boundary condition to the right. The thickness of the rod is capital D. Sorry, not thickness, the length. Initial temperature is some fixed temperature, and you have to prepare temperature distribution at steady state for the following data. And you have to prepare your project, and the result should be just a concentration profile at steady state for such problem. So time is on, and you have half an hour to prepare such project. Do it correctly. I mean that if there is a possibility to put some comments or probably change the name to the suitable one, which in your opinion is more readable than the standard description of COMSOL, do this. All right. Do you know what you have to do? I can't hear you. Hello?
I think we mostly know.
Okay. So see you in half an hour. you have this, and this is called next. And the next step will be the definition of the geometry. So we go to geometry here, right click, and choose interval. And you can see that, okay, and the description is just, I would say, left L. So this is why we changed this number of intervals to many, and now provide those points. 0 is the first one, L2 is the second one, and L is the third one. And if we click Build All Object, you will see an extra dot here. So it means that our geometry is composed of two intervals. And in the calculations, you will see time derivative of concentration. See future, we would overridden. If the formulas are not correct or the units are not.
Why is it lighting up?
Yes,
because
but we will do the, and the next step will be 1, and this is the default setting of the console. And now, what about the flux gamma? This A constant here in front of the second time derivative is 0. So it is exactly how we have in our case, because in our case we have only the first constitutive left concentration, left conditions, constitutive equations. So let us choose general form PDE, defined geometry as composed of two intervals. And the total thickness of the sample is of course L. The next step will be to provide information about the constitutive equations. So let us choose general form PDE. And you can see in the settings window, we have equation. When we click to equation, you can see what is the equations which will be solved by COMSOL. So have a look. We have second time derivative of concentration. We have first time derivative of concentration. We have divergence of the flux gamma, and we have the source term F. By default, COMSOL assumes that this A constant here in front of the second time derivative is 0. So it is exactly how we have in our case, because in our case we have only the first time derivative of concentration. So this EA is 0, dA should be 1 because we have no coefficient before the max way. So that will be concentration gradient. So why I have written Cx? This is why, because COMSOL usually use the following notation, which means that if we have expression like that, COMSOL, you have, please remember, put multiplied by issue operator associative equations to our problem, diffusion reaction problem. See our problem, diffusion reaction problem. As you can see, we have this problem is called untitled, yes. However, we call this diffusion reaction down, that it is just mass balance equation. If the sample and the right side of the sample, it is true. We have initial values. Right click. Is it clear now?
Yes.
Okay, good. Left. About this.
When I added the Excuse me.
All right. Are you ready with your project?
Well, we have some results, but
okay.
I have a
Who
problem.
wants to start to describe his or her project?
What do you mean by describe?
Just say step by step what you have done.
We don't actually know what we have done.
Sounds interesting, yes? All right. Okay, so can I have some more details?
I mean, we don't know if it's correct.
Yeah, that's my role to check it. However, please just tell me what you have done, so we will discuss about it. Okay.
So added 1D geometry object with
Yes.
2 intervals.
Could you share your screen, please?
Yes. 1 second.
Okay.
So
okay.
So I defined the parameters.
All right. So we have the length. Okay.
I know
we
the
have
round,
temperature on the left end and initial temperature. Okay, good.
They're off because I didn't see you define them at the end of the exercise.
Right, but okay, all right, okay, it's fine. Okay.
Yeah, and I chose material because it forced me to, so I chose copper.
Yes.
I added a geometry with 2 intervals.
But what was the reason to divide it to intervals, in fact?
Oh, actually, no reason. I just had troubles with selecting a boundary, so I thought it may help. Yeah, but actually,
okay,
this is fine.
Okay, right.
And I couldn't delete this default insulation, so I created another one and overridden it. Same goes for temperature at the left end.
Okay.
Yeah, and I changed the mesh to user controlled.
If you go back to thermal isolation 1, okay?
Yes.
You have thermal isolation 2. So please make it disabled, this thermal isolation 2, okay? Right click.
Yeah.
And you have disabled here.
Okay.
All right. And now you can see that when you provide the temperature, the first boundary is overwritten, yes?
Yeah, it makes sense.
But you have done correctly. It's okay. You can make it enable again. Enable.
But it's not necessary, right?
Make it enable, and now call this. This is thermal isolation, for example, right. Yes. So from the right, for the right boundary. Okay. And here this is temperature left. Okay. I think it's reasonable. Right?
Yeah.
What is the next step?
Changed mesh to user controlled.
To user controlled. Yeah, but may I see more details about heat transfer in solids?
Yes, and this is the thing I wanted.
If you go to solid 1, please.
Yes, and that's what I wanted to ask. no option to edit this equation or model unless
Yeah.
it's this option.
The reason for that is that you use this heat transfer model. If you
Well,
use general form PDE, you would be able to edit almost everything.
oh,
This is the price for using some predefined equations for the heat transfer.
I see.
And in fact, can you go to the bottom slowly? So I would like to see in this solid settings, okay? In the settings, all right.
Yeah, but there's no bottom.
All right. Just a moment. For me, it's bottom because I have enlarged the screen, so I see only part of them. So sorry for that. K from material, rho from material, CP from material. Yes. Could you go to copper? Yes, material, and just some material properties. Why not? And let me see. I would like to find out material contents. Could you open this press this triangle near copper to the left? All right.
So,
in the materials.
Yeah. Okay. Yeah.
Yes. All right. So click to basic. All right. So we have here CP, we have here density, and we have thermal conductivity. But as you can see, you can see, I will share my screen for a while. Yes. So this is our equation, and K is a
Sorry,
function.
but we can see your screen.
Oh, sorry, I don't know why. So let's do it again. Just a moment. Of course. Yes, I will do this. However, I think the important way how we can learn is just to analyze your work, because you can have quite different ideas. So I'm I would say this like that. I propose something when I give you some example, but it does not mean that it is the best solution. In my opinion, yes. So this is why it is interesting when you prepare something, because we can analyze this and probably analyze the different way of thinking, which is quite natural. Let us remind ourselves this problem. So K multiplied by dt over dx is just the Fourier flux. We need only minus here, yes? Here is some this 2v divided by r multiplied by t minus t odd. This is just the source for the energy equation. And as you can see, this coefficient, heat transfer coefficient, is described as a function of position, because this is K0 multiplied by 1 plus x divided by d. And the rest boundary conditions, I think, are quite natural for us. And we have some data. This K0, D, TL, TOT, R, and capital V. So in such a case, I will definitely recommend at first general form PDE for the preparation of for the solving of this problem. However, of course, you can use predefined physics like heat transfer. So we will try to analyze your case. So I will just a moment. I will make a copy of it to have it in front of me. Probably you have done exactly the same. All right. Okay. Here we are. Okay. All right. So I will stop sharing my screen, and could you share your screen again, please, with your project?
Yes, but I closed it, and I'm trying to make it again, to do it again in general form PDE. So which one should I open?
This one, which we've been analyzing.
Yeah, okay.
So with the heat transfer physics. All right. So as you can see, I will just a moment. But my question is, why you decided to use copper as a material? What was the reason? There is nothing in the model or in the problem to be solved that it is made of copper, this rod, or it is written there. It is written only that there is a heat transfer problem in the rod in 1D geometry. No copper is mentioned. Why did you assume that it is copper?
Oh, my microphone was off. It wouldn't compute without the material.
Well,
so I just
okay.
I was kind of
so at first I would just remove this material, remove copper here from here.
I mean,
because this is not our case.
Yeah, it needed
just copper, right click and remove, delete. Yeah. All right. Okay. So go back to solid 1 in heat transfer in solids. All right. And as you can see, you have here K from material, thermal conductivity from material, user defined. It's another option. Okay. So here you can just put this expression that it is K0 multiplied by bracket 1 plus X divided by D, close the bracket. All right. So let's go back to our properties. Properties, global definitions properties.
I'm sorry, will it work if we didn't define X?
What do you mean didn't define X?
Like it's yellow here.
It
because
won't have any...
X is a typical notation used for the position in console. So it is not necessary to define it. So please remove this X from here, because probably this was something like misunderstanding, because in the formulation of the problem, just a moment, because I lost my picture. All right, where is it? Where is it? Oh, it's here. Because the equation of heat transport, there is a derivative, d over dx. And in this expression for the k is also x, and it is exactly the same x. It means this is a position, all right?
Yeah.
Is it clear or not?
Yes, yes.
Okay, good. So let's go back to parameters. Let's go back to parameters because it is not everything. We have d. Why you put 1? D was 1.5.
Yeah, I didn't see the definitions. When I was creating parameters, I didn't see they are defined at the end of the picture.
All right, sorry for that.
Yeah,
1.5. Okay, enter.
Also the
TL is 70. All right. T tot. TOT is 50. All right. K0 is 60. All right. R, small r, is 0.25. And capital V is 20.
What descriptions should I?
Yes, K0, right here, K equals, sign equal. All right, thank you. K0.
In the expression or in the description?
Yes, exactly, expression. K0 multiplied by 1 plus.
Once again.
No, not here. Here is correct in the description because it will. This is K0 multiplied by. Is okay. K equals K0 multiplied by 1 plus X divided by D. Divided by D. Close the bracket. There is bracket. Yes. Okay. Now it's correct. And
so we just show it
expression for the R and V is just that it is source term. Right in the description, source term. And the same below. Okay. All right. So now let's go back to solid. Right. And all right. Source term. You're welcome. All right. But at first, go to study before we go to. And in the study, you have time dependent. Why? In this project, we are looking for a steady state solution. So click to study 1, right click, study 1, not test study, right click and delete. All right, and now go to the menu, study, choose at study, and
right.
When you click at study, what's going on? Nothing?
No, it works. It works. I added stationary.
Yes. All right. It is stationary now. So it is correct. Go back to heat transfer in solid 1. Okay, here. Right click to equation. All right. we have K defined as, and it is correct, density, choose density from material to user defined, and change. In fact, we do not have this information. Why? Because we are solving a steady state problem, and in a steady state problem, this term here, when there is we do not need this density, but put here 1, for example, and from heat capacity also user defined, and also 1, because they are definitely not 0. It shouldn't matter at all what number we put there, because in the equation, steady state heat transfer equation, there is in fact no density and no heat capacity. So now let us go back to our initial values below. And in the initial values, what is TOT? It's correct. Thermal isolation 1, once more. This is overwritten. Okay. Isolation right. Okay, it's correct. And temperature 1 is TL.
I'm sorry, but in thermal insulation 1, why both are overridden?
Yes.
2 is here and 1 is here.
Because we introduced another thermal isolation. Right-click to thermal isolation right. You can see that we have chosen as a selection the second node. Can you see it?
Yes, I also got it like that.
Okay, so it is here. So the node 2 was defined here. Let's go to temperature left. And this time we have chosen the node 1, which is the left one, left boundary. And it means that everything which was a boundary condition here was overridden, and the default one was thermal isolation 1. Click please thermal isolation 1, and you can see that those nodes, those boundaries are overridden by thermal isolation right and temperature left. Is it clear now?
Yes, thank you.
Okay, thank you. Also,
No, you can't. We didn't change it.
Thermal isolation means that temperature gradient is 0 or flux is 0. So in such a case, it is just this expression. So we do not need to change it. All right, and when it's done, we can go to mesh. Let's go to mesh. And at first, leave it as physics controlled mesh, okay? All right, let's go to study 1, stationary, and just click compute. Let us see what happens. Nothing is going on?
Yeah, it's finished.
Well,
but this
is the solution? Sorry, click stationary and click again compute. Whoa, it is really strange. It is really strange. Let us go back to we have. All right. Okay. So we will do it now differently, and we will see how it works. So in the same project, okay?
Yes.
In the same project, click in the menu for physics. All right, and add physics. And choose General Form PDE. All right. In this project, go to General Form PDE. Write dependent variables. No. In the settings, you have in the settings window.
Oh.
Dependent. This is U. Let leave it U. It's okay. It's okay. U means also temperature here. So let's go to General Form PDE below. And you have here this expression for the flux, yes? And this expression for the flux is UV is UX. And we have to multiply this by this expression K. So multiplied by K0 multiplied by 1 plus X divided by D. It's correct. All right. Source term. What is the source term?
Excuse me.
Yes.
In the conservative flux, the minus at the beginning should stay, or should we delete it?
Yes, should stay.
Okay.
Because this is the nature of the process.
Okay, thank you.
And in the menu, choose physics. In the physics, choose add physics. This in this ribbon. And after that, when you put it, please press it, add physics again, okay? And in the window add physics, choose General Form PDE or double click or add to component. All right. All right. And now source term in the near F, write please 2 multiplied by capital V divided by R multiplied by bracket U minus TOT. Because do not forget that in this case U is our capital T.
Will it matter that I changed U to T in heat transfer?
No. Okay. Because what we are doing now, we will, in the same project, we will solve this problem using different interfaces. One is this heat transfer in solids, and another one is General Form PDE. So we could do this as a separate projects. However, we will do this in the same project because we will be able to compare the results. And here, capital T means temperature for the heat transfer in solids, while in General Form PDE, temperature is called U. Is it clear?
Yes.
Okay, good. So we defined our source term, and okay, let us see equation here. Click to equation, and let us compare this with our problem, because we don't have this time derivative in our case. So it means that equation, so dA should be 0 here. Okay. And we have divergence of gamma equals F, all right? But gamma here is the flux.
Which one is gamma?
Sorry?
This one?
Yes, this is gamma. That's true. But this equation is, if we write it down, that it is d over dx from the flux, and flux is minus ux multiplied by k. But in the equation which was provided in the program, we have in the bracket that it is without minus. So it means that our source term should have minus here. So put near F, before 2, put minus. All right. So what is the next step? The next step is initial values. Click to initial values, and the value of U should be TOT, okay? TOT, all right. Next, add Dirichlet boundary condition. All right, and call it that it is left. Sorry, not particular. Right Dirichlet BC, Dirichlet right Dirichlet boundary condition. All right, okay, and choose. Sorry, boundary condition was at the left. Sorry for that. So this is left boundary condition, and choose the left boundary. So remove. Is it correct?
No.
Yes, now it's correct. And the prescribed value for the temperature for U should be TL, yes? Okay, good. Now click to zero flux. Right, so zero flux means that it is homogeneous Neumann boundary condition. Just write here that it is zero flux, but instead of 1, write right, okay? All right, so it's done. And now go to stationary and press compute. All right, and now go to results, right click, and add one dplot group. Where? But sorry, who is talking? Marceli? All right. You know, if you don't mind, I will answer your question in a few minutes, okay? I would like to analyze now the results for our project. So one dplot group, okay. In the description, change to, sorry, change to just U, because this is, and in the bracket put temperature temperature, general form PDE. Okay, and now right-click to 1D plot group and line graph and change expression to U. All right, and plot it. Oh, sorry, one more thing. In the selection, active, make it active, and choose the region. So, all right. And now plot. Here we are. And this is the solution. And if you go back to our temperature and press plot, we have different solution. Do you have any idea why?
No.
Really?
But I did get results in form of curves.
Yeah.
Previously.
When we go to heat transfer in solids and press solid, we provided information about thermal conductivity, but we did not provide any information about the source term. Can you agree with me?
Yes.
And this is the reason why our solution looks like this. So right-click to heat transfer in solids and change add heat source. And now in the user-defined general source, write 2 multiplied by capital V divided by R multiplied by bracket T minus TOT. Close the bracket and stationary and compute again. Oh, sorry, here choose selection. Sorry for that, yeah. Okay, and stationary.
All right.
And you can see the solution. Is it similar or not?
Yeah, it's different.
It's different. Okay, so go back to our source, heat source. I suppose that we should provide minus here in front of, yeah. And go back to stationary and compute.
So it's the same now.
Yeah. All right. So now you realize why I wanted to analyze your example and show all of you how it can be done using general form PDE. Of course, both attempts have advantages and disadvantages. So it's up to you which one you would like to use. And I think we will use both of them, sometimes general form, sometimes heat transferred, but we must remember that in the heat transfer there is some predefined values which sometimes can be misleading. And we must just carefully read what is provided there. Okay, Marceli, could you show your screen, please? Yes. So show me where is the problem. Multiplication. Oh. Oh, give me a second. Temperature left, which is no. As you can see on the, sorry, could you show? Yeah, below settings you have thermal isolation. Yes, so it is not temperature. This is still this thermal isolation. So please remove this heat temperature left. Okay, and right click to heat transfer and choose temperature here. And now choose the left boundary and change label to temperature left. Okay, and write down the temperature here, this T0, that it is just TL. Okay, and now let's go back to stationary and compute. All right? Yeah, definitely. All right. Okay.
Excuse me?
Yes.
What was the last step to make the graphs looks the same in the general form and heat transfer?
Right. Excuse me. Who was showing his project? It was Artur?
Yes.
Artur, could you send me your project to my email account, rof@agh.edu.pl, okay?
Yes, of course.
Right. Did you send it to me?
1 second, I have to log.
Right. Could you switch your camera on, please?
Okay, I sent.
Okay, thank you. I can see your faces. Okay. Thank you, Artur, once more. All right. Good to see you. I don't like those circles with some letters, to be honest. Okay, please do this. All right. So my question to you now is, shall I analyze the project which was done by Artur and a little bit with my help, or shall I do everything from beginning? What do you prefer?
I think that if you did it from beginning, it would be better because you could explain everything that you do and why.
Okay. Okay. So thank you for this comment.
Excuse me.
Yes.
Can I get the answer to how do we make those graphs look the same? Because Artur had the same problem that his general form graph was slightly different, and we changed that, and I didn't cut it. How?
Okay. Okay.
That one part.
So I will answer your question, and after that we will prepare. We will solve this problem using two different ways. Okay. One using this general form PDE interface, and another one using predefined this heat transfer interface. Is it okay?
Okay.
Right. So please leave your camera on, and I will try now to open the project provided by Artur.
Sorry, can I turn my camera off because I cannot do notes when I holding my phone?
Okay, good. Of course you can. Right. Please give me a second because the console must open the project. This. Right. I need some time. Okay. Okay, so I will share my screen now. All right. And and as you can see, in the component one, we have two interfaces: heat transfer in solids and general form PDE. And in heat transfer in solids, we added a heat source, and this heat source at first was without this minus here, and without minus, we really have different different behavior.
Oh yeah, I see. Thank you.
And what is a good idea to do is create something like comparison. So it means that we can add another 1D plot group. Okay, and now add line graph and Okay, we have selected the domain. It is very important, otherwise we will see nothing. And here is the temperature, right? And we can add in the same graph another line. This line will be U this time. And as you can see, the behavior is really different. However, when we put this minus sign here, which is now correct, and let us click compute, and let us go back to the comparison. I can't see my mouse. All right. And you can see there is no difference. Why? Because they are exactly the same. You can see in the description that we have line graph temperature and line graph dependent variable U. So there are two curves here, but they look exactly the same. All right. Coloring and style we can change. So instead of solid, we can choose dotted. And where is the yes? Can we see something more or not? Let us see. No, still not. Cycle, color. Let us change our color to red, for example. And it is dotted, probably dashed would be better. Right. And what is the thickness here? Right, let's see it again. You can see two colors now, I think, because one is this blue and another one is red. So we can choose legends also. Yes. And this is those solutions match perfectly. So we obtain exactly the same solution using different interfaces. We're using different ways how to solve our problem. And I remind again this problem. And in fact, to write it properly, it would be better to write minus here, because now it is the flux, but we also must put minus here. And this equation, of course, from the mathematical point of view is exactly the same. However, now it is more physical, because expression in the flux is expression in the bracket is the flux. Without minus, it is not the flux, it is minus flux. So we must remember about this. Is it clear?
Yes.
All right.
Can I have one question?
Of course.
If our source is negative, it means that our rod is cooled.
So if the source is negative, it means that the temperature should decrease. That's right.
Okay, thank you.
Yeah. All right. So now I will start a new project. Okay. Just to see. Let me be allowed to. Just a moment. Okay. Right. So. All right. So we start a new project. This is one-dimensional project, so we choose 1D here as a space dimension. And probably I will start from general form PDE first, okay? All right, so general form PDE, add. And I use U as temperature here. And study, and we choose stationary. And done. In fact, I could do slightly different. So I will go back, choose new, and 1D again, general form, and also heat transfer. So I will choose both of them. Study, stationary, and done. Do you have it?
Yes.
Okay, good. So, of course, we should start from parameters. So please remind me parameters. So this is definitely D, which is 1.5, as I remember. K0. Oh, sorry. 60. All right, here 1.5. Okay. This is okay. Equals K0 by 1 plus x divided by d. All right. We should have some R.
TL is 70.
Sorry,
R,
TL
TL
is
70.
70. All right.
TOT 50.
TOT 50. All right. What is R?
R is 0.25.
0.25. Okay, thank you.
And capital V is 20.
Is 20. Right. So I won't put description here, okay? Or you want left temperature
I think it's fine without description.
All right. Okay. So we have this all the data which are necessary, and now geometry. Right click, interval, and 1 is enough from 0 to capital D. Okay. Because as you remember, when we have different initial conditions, so we divide it in such a case to easily provide this more complicated initial condition. However, now the initial condition is exactly the same in the whole domain. All right. So we have defined our geometry. Now general form PDE, and the general form PDE, we have no this term du over dt, so dA must be 0 as well. What is the flux? Flux is minus, this is this k, so this is k0 multiplied by 1 plus x divided by d. In fact, the second bracket is not necessary here. And this coefficient multiplied by the gradient of U, of temperature. So this is our expression for the flux. Right. This is our expression for the flux, and we also need this expression for the source term. So 2V divided by R with the minus sign. Okay. Please correct me if I'm not right. Minus V or 2V divided by R multiplied by U minus TOT. Is it correct?
You missed the multiplication sign between 2 and V. Oh.
Thank you. You are right. 2V. All right. 2V divided by R. It's correct. Okay. All right. So we defined our equation and our energy equations, and also our constitutive equations for the flux and for the source term. And now initial values. Initial values is, what is the initial value? The initial value is exactly the same as TOT. Initial temperature is TOT. So let's go back to initial values, and this is TOT. And zero flux, it's now everywhere. We know that it should be only to the right, but we cannot remove it, so we change it, introducing the second boundary condition, Dirichlet boundary condition, to the left. Where is it? Oh, yes. Left. And the temperature is TOT. Okay? Sorry, this is left, so this is TL. Sorry for TL. All right. So we are almost ready with this first one. So let's go back to stationary and What's wrong? In solid, yes, because this interface is not, I will make it disable. So in such case, I hope we will be able to perform calculations, yes. And this is our solution. It's looks very nice. So it is exactly the solution of our problem. But it was done using general form PDE interface, yes? So general form PDE, so interface which can be adopted to our particular model. And COMSOL provided another possibility because quite a lot of people deal with some heat transfer problems. So they prefer use some predefined values, and those predefined values means here that, for example, they can use heat transfer in solids interface. And in such a case, the equation which describe this problem is generally, you can see some expression which takes into account convection, because U here means convection, and we have some sources which are described in the documentation of this model. So different aspects of heat transfer. So this is why I said that it is not so easy to start at the beginning, because you have to read the documentation. So some elements are prepared, are ready, but you have to understand what the particular terms mean in this heat transfer in solids module. As you can see, there is some different introduced descriptions. Yes. And how to adopt this heat transfer to our particular problem? What has happened that you disappeared and I can see only Patrick, and Susanna? Why did you disappear? Okay, thank you. All right. So at first, there is a default interface called solid. And in solid, we define some heat conduction, which is described by thermal conductivity. And this model, heat transfer model, usually works with properties defined by materials. So if we had really information that this material is composed of copper, so we could just choose defined copper as a material, and program will take data from this information provided by material. But we haven't got a particular material. We know the properties of material, but it is not defined in this model. So we have to use here user-defined conductivity. And it is, as we know, K0 multiplied by 1 plus X divided by D. Also, because thermodynamics is included, is a part of the heat transfer because we have heat capacity there, we have density in the full heat transfer equation. So it also should be provided in general, but in our case we haven't got this information. So we should provide some. It's better to give non-zero numbers. So I prefer to put 1 here, but it shouldn't matter if I leave 0 here. So we defined SAR now only constitutive equation for the heat transfer, but if you want to add source term, you have to add it. Right click and choose heat source. And heat source is added, and now this heat source, we must provide the information about the domain. So right click to our domain, and now you can see this heat source is this Q, and in the equation this is that Q is Q0. And let us go back to solid 1. What is Q here in equation? Q is just Q is this part here. So this is our one of the possible sources in this model. So we know that this heat source is like that: -2 multiplied by capital V divided by R multiplied by T minus TOT. You must remember that in heat transfer in solids, the name of temperature is T, capital T. But in general form PDE, we couldn't have exactly the same name for the variable, for the temperature. So this is why we used the default one, U. All right, so we defined heat source. We need Dirichlet boundary condition, which means exactly that we have to set the temperature. So temperature to the left, so temperature left, and the temperature is just TL. And heat at thermal isolation at the right boundary is what is correct, because this is also in our model. So we have defined the same model using 2 different interfaces. We can now compute both of them at the same time, because program does not recognize that it is exactly the same problem. It is not so clever. So we did it. We know that it is the same problem, but it is solved as 2 independent problems by COMSOL in the same project.
Okay, excuse me, but could you tell me why on the for the right side we choose thermal insulation and for the left side temperature?
Because this is how our model is formulated.
Oh, okay. Thank you.
So the most important thing is the formulation of the model. And this formulation of the model we transfer to COMSOL. And it is very important, of course, to understand different aspects of COMSOL to properly transfer the original model from the paper to the COMSOL. Okay? All right. Thank you, Agnieszka, for your question. And now let us go back to our solution. Because, yes?
I ask you to show the temperature left?
Sorry?
Can you show the temperature left?
Temperature left.
Yes,
All
no,
right.
in heat transfer and so on.
Okay.
So, is it a problem that our TL unit is in Kelvin degree, or it's not a problem?
But this temperature is in Kelvin.
No, yes, but at the right you have a key capital letter.
Just a moment. To the right.
No. Back to the temperature left.
Yes.
You have yes, and right. Oh, yes.
Probably, as I understand your question, is this temperature here provided in Kelvin or in Celsius? Yes?
I mean, I know that in parameters it is Celsius degree.
No. If we do not provide a unit, it is always SI unit.
Okay, I understand.
The SI unit for the temperature is always in Kelvin.
Okay, thank you.
So you must be very careful here. So in fact, yeah, all right. So this is this first graph is, as you can see, is this U. So this is just U general form PDE. And we will just duplicate this and will be temperature and heat transfer in solids model, and this time we have to change the expression for capital T. And of course, no changes, because they are exactly the same. And if you want to compare those results, you can create an extra graph or modify an existing one. So the first one is just temperature. So I duplicate it. Or what I can do, I can just plot the difference between T and U. Why not? And you can see that they are not the same. But from the calculation point of view, they are. Because as you can see, the differences are at the level of 10 to minus 12. But it is just numerical calculations, because usually when the values looks exactly the same, there are always differences. But the key point is what is the magnitude of these differences. And this magnitude is now 10 to minus 12. Is it clear?
I'm sorry.
Yes.
But my heat transfer results are strange. They stay at 70.
Could you share your screen with us?
Yes, of course.
Please do this.
Okay, can you see it?
Yes, just. All right. Let me be allowed to see your. So show me your solid, okay? Okay. Right click to hit source. Just left click. Okay. This is 2VR. Looks correct. Let us see temperature left. And this is TL, okay. Thermal isolation right. Also correct. So let us go to your plots now for heat transfer. Yes. Oh. Could you go back to stationary and compute once more, okay? And let's go to, yes, just a moment. Expression is temperature. All right. Oh, this is slightly strange. Let's go back to heat transfer in solids once more. Right click to heat source. Yes, in the selection, you have to choose the domain. And now repeat calculations. All right. And go back to.
Yes. Thank
all
you.
right. You are successful now. All right.
Excuse me, can you show your heat source one?
Who are you talking to?
Tomasz Myćka.
Sorry?
Tomasz Myćka. But
Right.
I don't have turned on my camera because
So,
of the new actualization of Microsoft Teams. My application don't recognize my camera on my notebook.
All right. Just a moment. Okay. So you mean this heat source, yes?
Yes,
Here?
yes, because
how to edit?
No, I don't have Q value.
Right. So
I have 0, so I would like to.
But this is exactly here. So this is minus 2V divided by R multiplied by T minus TOT.
Okay, I have it. Thank you.
Yes. Yes, please do this. Not yet. Now, yes. Okay. Right. Okay. show me 1D plot group 1. Yes, so press this triangle to the left in 1D plot group and click to line graph, and this is you. Okay. So something is I think wrong. Go to 1D plot group u minus t, and just a moment. And this is solution, right? Okay, and this is so at first go to line graph 1 below and change it to t, expression to t only. All right, and plot now. So this it is not working. So go back to heat transfer in solids. Go to solid 1. All right, and I would like to see the bottom. So right, this is user defined. Just a moment. K0 multiplied by 1. All right, X and D. This is correct. This heat source, please show me your heat source. All right, 2D looks okay. Show me your initial values. Change it to TOT. Okay, and now let's go to the temperature left. This is TL, it's correct. And thermal isolation. Okay. And now go back to study 1 stationary and press compute. And let's go to the second graph. Still nothing is here. All right. Oh,
There's
here.
nothing in the selection.
Yes, yes. Change the selection to the domain. You're right. Right click to active. Yeah, it's okay. And now go back to 1D plot group and press plot. No, here. Yes. Now it's correct. So go below to line graph and press in the expression, write u minus t minus u and plot. That's strange. Well, sorry. Do you think that it will be a big difference? Only the sign will be different. What is? So we have to go to general form PDE. All right. All right. Okay. Go to the bottom. Correct. Go to initial values. This is TOT. Correct. Dirichlet boundary condition. This is TL. It's correct. Zero flux. And it should be correct. Haha. This is a surprise, you know. Oh, what I would suggest, please send your project to me, because when you share the screen, I can't see properly because the letters are small. So please send the project to me, and I will look at it quickly and find a solution. Okay. All
My
right.
comparison also don't look like yours, doesn't look like yours.
So send me your project also. Okay.
Okay.
Yes. Exactly. All right. All right. So before I find the reason of differences, please let me know. I'm talking to all of you. Whether now the implementation console of those two interfaces are were understood by you, and it is clear, or I should explain something more.
If you actually think and put the right values in the equations, then it's pretty easy, but you have to think about putting those values and those equations in the right place. So that's the tricky part.
Yeah, you know, usually I recommend to use general form PDE, because you have in fact defined everything, but it is clear, I think it is more clear what to do. When you use, for example, this heat transfer in solids, you must learn more. Probably it is more efficient, but still you have to learn something else. So my recommendations, especially at the beginning, is just to use general form PDE, and when we are familiar with this, use other interfaces in COMSOL. I can't see any mails from you.
I sent it already, so it should be here.
All right. Yes, I have. Yes, I have emails from you now. All right. So I need a while, and in the meantime, I have a new job for you. Okay.
And maybe some break right now for coffee.
Good idea. If you like coffee, it can be coffee. Why not? All right. So how long do you need? 10 minutes?
10 minutes is fine.
Okay. I don't know whether it is enough to prepare the proper coffee. However, I'll do my best to do it as fast as I can. What a nice dog. It's he or she?
It's he. Thank you very much.
All right. Looks clever. So, all right. So,
I mean, he's certainly more clever than the owner. I can tell you that much.
you know, I would say differently. I like new pupils. So, all right. Okay. So, see you in 10 minutes. Hello, are you there?
Yes.
Yes.
All right. Okay, so we'll start from this projects with some differences. I will share my screen now.
I was able to find my mistake, but I don't really get it. Why does it work like that?
Okay, so you will share your screen shortly, but I will start from Mr. Hryniewicki, and I hope you see his project. Yes.
Yes, we can see it.
Yes. So the reason for that is in the general form PDE, it should be bracket here. Okay. That's the reason. So when you compute now, and we'll go back to your comparison t minus u. So now should be all right. It's perfect. It's 0. Yeah. So here in the definition of source term, because there was without brackets here. Can you see? Should be bracket here. All right. So I close this project now, and could you show me your Agnieszka, could you show me your project and
Yes,
indicate
of
us
course.
where you're gonna find those differences?
Can you see it now?
Yes.
Okay. So difference was that in initial values here, I had 2 OT, and others had 293 and 0.15.
It shouldn't have influence here.
And now it looks like this. But before you said that it should be 0. So I don't know.
What should just a moment.
This is a comparison.
I will open your project. All right. So I will share my screen now. Okay.
Okay.
I think it's opening. Yes, it's opening. All right, so you said that this behavior is different that ours, yes?
Yes, I mean, I changed in heat transfer in solids in initial values temperature.
Mm-hmm.
You can see that here I had TOT and now
Yes.
it's 293.15, like it was
Okay.
before.
All right. You know, when we analyze this problem, you should ask me, or you should just tell me. It's a better word. You should tell me that if we have a steady state solution, in general, we do not provide initial values. Is it
Okay,
true?
so now it's like it was before. I mean, before I change it. So now it should
Yes.
be fine.
You know, in practice, when we calculate steady state, the initial conditions should not affect the solution, because a steady state is a certain type of solution, the only one which does not change with time.
Mm-hmm.
But in practice, when we do numerical calculations, different algorithms can start from something. We call this also initial values. So when we start from slightly different place, we obtain slightly different results. But this slightly here means 10 to minus 12. So if the differences is in the range of 10 to minus 12, so we can assume that those results are the same, because these differences are so small, so we can completely neglect them. Because if you look at the graph like here, and also here, of course, we can't see the difference. The difference is at the level of, as you could see, 10 to minus 12. So now it looks like this. But generally, those values are really very, very small. So your project is correct. So in fact, in this formulation, we should not provide initial values at all.
Okay, but how did you do that your graph was constant at 0 point?
You know, I think this is the consequence of that. At first, I change it to t, and after that, it looked like this. But the reason for that is probably that COMSOL just signed some range of values, and of course we can change it, because this is always a way how it is displayed. If you want really to find out what are the differences in numbers, you can go to derived values here, right click, and let me see, I would like to calculate I would like to see, just a moment, I would like to find out the solution. I would like to export data, so data sets. I would like to have this one. I would like to, or let us create a table, probably will be better. And presentation format, model, column, header. Let us I would like to export now. I would like to export the results in the form of table. So probably this one is better. I can calculate, for example, the average value of the error. So we have here T, U, and we will take T minus U. All right, just a moment. T minus U here. Oh, there is no region here again, right? And evaluate. And now you can see that the difference between T and U, average difference, is less than, how many places have we got here? 4 places. And here we have some average values of the temperature in this region. So what I wanted to say, that the 0 here, or sometimes if I create a new graph like here, 1D plot group, and add line graph, and now put T minus U here. This time it is all the time 0. So this is below the error which can be recognized in console. However, as you could see, sometimes the values are 10 to minus 12. So it means that are very, very small. So if they are 10 to minus 12, or it is just constant, so you can assume, and it is 0, so you can assume that those differences are negligible. That concluding, both solutions using heat transfer in solids module or general form PDE interface give the same results. The error is negligible.
Okay, thank you.
You're welcome. You know, now I have extra job for you. So we have another problem to be solved, and let me be allowed just to give me a second. This is our problem. We have a certain ring, where we have some description of the model. We have Dirichlet boundary conditions. Okay, initial temperature is like that. So, and we have to calculate the temperature distribution. Let us calculate temperature distribution, and two cases. One is as function of time, and the second one is steady state. So in the first case, this will be exactly like this. And in the second case, I will forget about this because you know, but the second one will be just temperature as a function of xy. And here we have the parameters. Right. Okay, probably like this one. And parameters on the domain geometry are like, okay. So this is your job. Please prepare a project which solve the following problem. Okay? Is it clear?
Yeah.
Yes.
At first, please use general form PDE, okay? Use general form PDE, or all of you who has just odd computer numbers, use general form PDE, but for even numbers, use this heat transfer in solids, okay? And we will compare the results.
Again, which number, which...
Can you repeat?
Sorry?
Can you repeat?
Oh, I don't hear you.
Can you repeat?
Can I repeat? Yes. So odd numbers, it will be general form, but for even numbers, it will be heat transfer in solids.
Okay.
All right. So now you have 20 minutes and you work individually. All right.
Sense. And how do you think I?
Or you
point.
you are, but also just to create the proper equations, which okay, how are you doing? Did you manage to prepare the project?
Not exactly.
Not yet.
All right. All right. So a quick hint, we'll continue next time, but for those who are interested in, just give me a second. Right. Do you have 5 minutes, or we should just finish now?
Yeah, we've got 5 minutes.
All right.
Unfortunately, I do not have. I have to go to another meeting.
Okay. All right. So we will continue next time. So don't worry. I will repeat this. Okay.
Yes.
So thank you for your contribution. Okay. So very quickly, we have 2D and general form PDE. Study and let's say at the beginning stationary. And you mentioned about geometry. So please just tell me the parameters. What was A, what was B? Okay.
Centimeters.
What centimeters, yes?
Yeah.
Yes.
So 0.1.
All right. What was B?
6.
6, yes?
Yes.
Okay, thank you. So in the geometry, let us create ellipse with A and B. Okay. We'll create another one by duplication, and the size was twice smaller. Okay, and now we have to subtract them. So in the geometry, choose Boolean and partitions and choose difference. And we will, from the big one, we will subtract a smaller one. So as a result, we have such geometry. Okay? All right. So please save your projects and we will start. Sorry?
Can I have one more question? Just a small one. What was the okay. I don't have a word. What was the jednostka of CP?
Unit of CP?
The unit of CP.
Yeah, okay. The unit of CP is generally joule per Kelvin per kilogram.
Okay, thank you.
You're welcome. All right. So thank you for today's meeting, for your contribution, for your active contribution, and see you next week. We will start from this project. So if you can, please practice after 8 p.m. And we will just do this project step by step next week. All right. Thank you very much,
Okay,
and see you
thank
soon.
you. Bye
Thank
bye.
you. Bye.
Bye bye.
Thank you.
Thank you very
Bye.
much.
Thank you. Goodbye.